But I definitely go front. Let's go pause it. All right. That's true. Toss me that good back. I really about it. Not talking about this. I thought there was more problem. What's your background? Because I'm teaching now. Have those we had it one in
Hey, let's go ahead and get started. Is that loud enough, those in the back? Yeah, okay. We're talking about conductors today. I went out and got myself a pair of coveralls. The fact that I could find a pair that fit me was amazing. It was a tender mercy. Would anyone be willing to give us an opening prayer this morning? Thank you, sir.
Our dear Heavenly Father, we are truly thankful for this day. We are thankful so much for the weekend we were able to have to be here in Professor Francis's class. We're grateful for thy tender mercies this day and the opportunity we have to talk about physics. We pray at this time for thy spirit to be present, that help us to feel prompted to ask questions and to be inspired by thee this day, and that all of our concerns will be able to be answered in good time. And we say this in the name of Jesus Christ. Amen.
Amen. Thank you, brother. Okay, I hope that everyone has internalized this two-step dance that we're doing every time we try to find electric force by one thing on another thing. There's always a pusher and a pushee, okay? And the two steps of the dance are, first of all, the pusher, the source charge, sets up a field, changes the room. And we went through a method of visualizing that field last day with electric field lines. Once the field is set up, then that field pushes on the pushee, the test charge. Okay, and that's always going to be through this equation right here, which is the operational definition of the electric field. Now, so far we've only learned one way to set up an electric field, and that's the field due to a point source, concentrated charge. Today I'm going to teach you two other ways when the charge looks different, and no matter how we find that electric field, by hook or by crook, we can always plug into this equation to find what we really care about, which is the electric force. See if your neighbor understands the difference between field and force. Talk to your neighbor.
I guess the where you from? Calculated and
We're going to be using the idea of symmetry today, and I've spoken about this previously. Symmetry is the idea that if the problem looks the same when I stand on my head, the solution needs to look the same when I stand on my head. And that's why I like this cartoon. One day, Wilson, I'll be sitting at that desk. You can't tell the two desks apart. And that's why we laugh. Okay. Laugh. Say it with your happy face. I love this one. Zur falschen Zeit am falschen Ort im falschen Job. At the wrong time, in the wrong place, in the wrong job. Okay. You know which one's saying that. So just as a quick review, we use these electric field lines to paint the picture of the electric field. And where the field lines are close together, the electric field is strong. The stink is great. And the direction is going to be tangent to these field lines. If I'm looking between field lines, I kind of average the directions here. Now, in your homework that's due tonight, there were some cases where you needed to find the direction tangent. And you know, it was kind of iffy. You know, depending on how you put your ruler, it could have been here, it could have been there. In those cases, I set any answer that looked reasonable as correct. Okay, and if you choose any of those that are, you know, ballpark, it's going to give you full credit. If you choose something wildly different, it's going to come back and say you're wrong, but it's not going to tell you what the right answer is, because at that point, Max doesn't know anymore. Because Greg was wishy-washy. Okay, if you give it more than one right answer, Max just throws up its hands and says, I don't know. Okay, so don't be disturbed if the message comes back. I can't tell you what the right answer is. Now, likewise, if we go up here, I've got a shorter arrow representing a weaker electric field because the field lines are further apart, and here they're really far apart. So I get a much weaker field. Okay, I hope that that's so basic that you're bored. We're going to go someplace different now. Suppose I went down to Lowe's and I got that charged paint, that positively charged paint, and I painted this tabletop. And suppose this tabletop was huge and I just kept on painting, and I was really careful to always make the paint the same thickness. Now, that thickness turns out to be an important quantity. We call it the surface charge density. And we use the symbol sigma, that's a Greek S, to represent that. And it's just going to be the total charge. This would be the source charge divided by the total area. In other words, it's how thick I spread the paint. How thick I spread the paint. Now, what you're seeing here is a sheet of charge. It looks like a line because I'm constrained to this screen, but you need to imagine this being a sheet that comes out and it goes over your heads, but it cuts their heads in half. Okay? And it just keeps on going out towards you and away from you as well. Infinite sheet. Okay? Now, Haley? Elizabeth, I was so close, wasn't I? Maybe Elizabeth. Elizabeth. I claim that that's one of the field lines due to this vast sheet of charge. And I'm picking on you because you're right across from me. And when I look at the problem, that's the charge, I see a great big flat sheet of charge going off forever. And when you look at that sheet, you see the same thing, big flat sheet going off forever. Now, I see a field line that goes up and to the right. Is that what you see? up and to the left. Okay, so Elizabeth and I see the same problem, but we don't see the same solution. And that's what tells me that this cannot possibly be a correct field line. Now, I'm gonna say that that's a correct field line, because I see the same problem that Elizabeth does, and she and I see the same solution. It goes straight up. Fair? Okay. Now I'm gonna put the next one in. I'm gonna say for the same reason, it has to go straight up. And then I'm gonna put the third one in. And suddenly we have a problem again. Elizabeth and I see the same problem, the same sheet of charge. But I see that the spacing is getting bigger as it goes to the right. And you say bigger as it goes to the left. So again, Elizabeth and I see the same problem, but not the same solution. This cannot be true. So the spacing has to be the same in both directions. Are we on the same page there? Does that make sense? And indeed, if I kept on going, I would have to have the same spacing. And if I could have afforded a bigger board, it would have just kept on going. But we're a poor school. We're not a poor school. Just saying. Okay. So I'm going to just put these in here. And I've done my best to try to make these evenly spaced in as many directions as possible. And so two of the holes wrong, and so they have to have this tape to hold them in. That we spared no expense. Okay, so now you see that pretty much no matter which way you look at it, the spacing is uniform. Okay. Now, I claim that that's what the field lines look like for a sheet of charge. And so let me put those up on the screen. That's going to so there's my first one, and there's the rest of them. Now, again, symmetry suggests that this sheet of charge looks the same whether I look at it from the top or whether I look at it from the bottom. If I think of this charge was being painted on, say, a big sheet of saran wrap, you know, like you buy at Costco and it lasts for 15 years. Well, then I would have field lines going the other way as well, away from a positive source. See if your neighbor believes that those are the field lines due to this sheet of charge.
I can get behind it. You believe it? I mean, I follow the NBA a lot, but I'm not. Oh my! Wait, are you stand? Yeah. I'm from the team.
I respect that.
Now,
They are.
we never really encounter an infinite sheet of charge. They're too big to carry around. And so for a finite sheet of charge, what we get are field lines that kind of curve away. But it turns out that a lot of physics is done very close to the surface of a charged object. And if I'm really, really close to the surface, what that looks like is what we've got there. Okay, and the question is, how close is close enough? Well, you have to be close enough so that this distance to the surface is small compared to the distance to the edge. In other words, you have to be, towards the middle of the sheet and fairly close to the sheet. But that's where a lot of physics happens. And so we call that the infinite plate or infinite sheet approximation. And another way of thinking of this, I like this cartoon, face it, Greg, you're lost. Okay, if you're close enough that it looks the same in all directions. Imagine a tiny, tiny, tiny amoeba right down here in the middle of that block of wood. When it looks around, it just says, whoa, it goes on forever that way. Whoa, it goes on forever that way. It looks the same in all directions. Now, this is the most important question you're going to be asked today, unless someone asks you to marry them. Okay, this is it. Suppose I were to tell you that the electric field right there was 5 newtons for each coulomb. Okay, that's a given. That's a given. The question is, at this X up there, is the electric field going to be bigger than 5, equal to 5, or smaller than 5? Get your clicker out. Okay, now you can click.
I think so. Equal.
So kind of like farther away, so I'm just like
Okay, rocket science, we did that last. Well. Oh. Okay. So. We have this person that's just messing with me. And then we have 2 groups. We have what I like to call believers and unbelievers. Okay. And you know which category you're in, whether you're a believer or an unbeliever. And when I say that, I mean believer in field lines. Okay, these people believe field lines, these people not so much. Now, some of these people in the believing pile may be like that father of the possessed son who said, I believe, help thou mine unbelief. Help me understand why I believe field lines. Why should I believe field lines? So let's help your unbelief. First of all, let's try this. So I claim that that's going to be exactly 5 newtons for each coulomb. If this is 5, that's 5. Because the spacing here is exactly the same as the spacing there.
Yep.
And some of you are saying, Greg, that's crazy. That's crazy talk, because this one is close to the charge and that one's far away from the charge. How can they be exactly the same? Because I believe in field lines. Okay. Now, let's look at 3 different ways to try to help you believe in these field lines. Okay. First of all, I put a wall here and you can't see what's causing that that field up there. Oh, let's do this first. For what doth it profit a man if a gift is bestowed upon him, and he receive not the gift? Behold, he rejoiceth not in that which is given unto him, neither rejoiceth in him who is the giver of the gift. Okay, I gave you the gift of those field lines. And the unbelievers threw those away and they just said, hey, look at the charge. This one's closer to the charge, bigger field. That's what works with the point source. And you went with that. Okay. Now, we could also create these fields with a negative sheet of charge up there, could we not? It'd be the same. And if that were the case, the unbelievers would want that one to be the bigger field. When I had a positive sheet down here, you wanted this one to be the bigger field. When the negative sheet's causing that electric field, you would want that top one to be bigger. Since we don't know which of those sheets of charge created those fields, it doesn't make sense that, well, sometimes this one's bigger, sometimes that one's bigger. See if your neighbor bought that argument.
That's valid.
You guys are spaced out.
So
Yes. Basically, you
Okay,
found that this statement about the top is going on. You would argue that the top one is longer.
I'm
Thinking that.
gonna take 2 more kicks at this can.
It's not-
So that I can convince everyone in the room that the electric fields are exactly the same at those 2 locations. The result is that near a plate, the electric field does not vary with distance from the plate. For plates, we get this formula here. To actually derive that formula, we would have to go through a lengthy discussion of Gauss's law, which I believe is the second most beautiful law in the universe. But my experience over the years is that if I were to spend 3 weeks trying to teach you Gauss's law, we would still have a disaster on the exam. So this is the result. And that epsilon naught we call the permittivity of free space. And it has the value 8.85 times 10 to the minus 12 Coulomb squared over Newton meter squared. And that will be on the front page of the exam, that number. But it's one of the basic universal constants. I mean, there's not that many of them in physics, and that's one of them. Now, we found for point charges that we had a very, very different formula. For point charges, it depended strongly on the distance away from the charge. Twice as far away was 1/4 as strong, 3 times as far, 1/9 as strong. Where here K was 9 times 10 to the 9. Now, you see that there's no R in our formula for a sheet of charge. So I'm going to put that formula up here. So if I have a single sheet of charge, sigma, I'm going to get a field that's equal to sigma to epsilon naught. And again, we have the same rule for the direction of the electric field as we have for the point source, away from a positive towards a negative, away from a positive towards a negative. Now, let's take another kick at the can. Suppose that I take that sheet of charge that comes out and goes right over your head. Suppose I divide that up into slats, kind of like in a hardwood floor in a gymnasium. These slats come out towards you like that. Are you seeing it? Are you seeing it? Now, if I put a little test charge above that floor and I look at the contribution of the force on that test charge, and I'm going to look at the contribution due to this charge slat and this charge slat. Okay? Now, they're fairly far away from my test charge, and the angle that they're pushing with is kind of fighting each other. And so the contribution that I'm going to get from those two slats is going to be fairly limited, both because they're far away, but more importantly, because they're not pushing in the same direction. You've seen that argument before when we had this semicircular rod, okay? Now, on the other hand, if I were to look at the contribution due to these two, what I would get is something that was, first of all, bigger forces because they're closer. And then because they're pushing in more the same direction, I would get a humongous result when I added those two vectors. Everyone good? So what I'm going to do is I'm going to define a cone of influence, kind of like the cone of silence and Get Smart 2 old way back there, Maxwell Smart, okay. The cone of silence. The charge, I just went 45 degrees. I chose that randomly. But if I just choose a circle of charge that is 45 degrees down from my test charge, I'm going to say that charge inside the circle is going to be the most effective at pushing on the test charge. Does that make sense? Okay. Now, if I move that test charge up there, two things happen. First of all, my test charge gets further away from the charge inside the circle. Okay, now the circle, the cone of influence, is going to be that big. So I just did two things. First of all, I increased the size of my circle of the charge that's pushing in the right direction. I also put the test charge further away from that charge that's pushing in the right direction. Now it turns out that the push by that charge drops off as 1 over r squared. But the size of the area inside my circle increases by r squared. And the two effects cancel each other out. So I get exactly the same push when that test charge is there as when it's there. See if your neighbor followed that reasoning.
Such a good way to saying that.
And also you get the same push no matter how far compared to there. That's so many, I don't know if that's true of other angles, but that's the most, I guess, what you can get.
Okay,
That makes sense.
questions?
Because the area.
I get one more kick at the can. Many years ago, the provost at Montana State University was a physics professor, Jack Drumheller, a friend of mine. And Jack was ancient, and he had been a fighter pilot during the war. And he claimed, he shared with me, that during the war over the Pacific, planes were shot down. And the pilots had to bail out, and they had to use their parachute to come down safely. And that those pilots, when they were shot down, would hope for a windy, stormy day. And the reason for that is that as you're falling with your parachute, you don't want to land in the water with your parachute attached to you, because then you're going to land in the water and your parachute's going to land on top of you, and it's just gonna drag you down and drown you, okay? What you wanna do is you wanna release yourself from your parachute and drop the last 20 feet so that you can swim out away from your parachute so that it doesn't land on you. If it's a nice calm day, the water looks like glass. And it looks exactly the same when you're 20 feet above it as it does when you're 100 feet above it. And if you get confused and think you're 20 feet above when you're 100 feet above, you're going to drop and break your legs. Okay? And so they hope for a windy day where they can see waves and they can say, okay, that wave's, I hope, about 5 feet high. I might be 20 feet high. See if your neighbor bought that third explanation.
So are we saying this is like product-filled?
I was just kind of. And not apply.
I think we're saying like you can't tell the difference between where you buy it.
It all looks the same.
If we take that example to our sheet of charge, if I am this far above that sheet and I look down, it just looks like an infinite sheet in all directions. If I'm this close to the sheet and I look down, it just looks like an infinite sheet in all directions. If the problem looks the same, whether I'm here or whether I'm there, the solution, namely the electric field, needs to be the same. Now, if that sheet is not infinite, if it's only this big, then it looks very different from here than it does from there. And then all bets are off. Then the electric field's not the same at both places. But if that sheet's big enough that it looks the same in all directions, then we have the infinite sheet approximation. Okay? Now, I hope that we're all believers in field lines now, because that's going to make life so much simpler. Here's a problem in your homework that's due Friday, associated with today's lecture, 4-2. We have a square plate with sides 2 meters on each side. It's laying flat on the floor. The plate has a uniform total charge of 65 microcoulombs. What's the electric field 1 centimeter from the surface of the plate? What words are not needed in part A? What words are wasted on that part A?
1 centimeter?
Yeah, 1 centimeter from the surface of the plate. Could have been half a centimeter, could have been 2 centimeters, could have been 3 centimeters, okay? It doesn't matter. That's the key. So, let's work that. First of all, we always find the surface charge density. If I take the total charge, which is 65 microcoulomb, or 10 to the minus 6, and I divide by the area, it was 2 meters by 2 meters. That's going to be an area of 4 meters squared. I get 16 microcoulombs per meter squared. I then find the electric field by my formula over there. I divide by 2 times the permittivity of free space, and I get this value that value is not that important. The process we use to get it is important, okay? 9.2 times 10 to the 5. Now, again, in maths, when you go to do your homework, you're going to get a different value for the charge. It's not going to be 65, it's going to be 69 or 63 or something like that, okay? So your answers will be slightly different than this. Now, we just did step 1 of our 2-step dance. We found the electric field caused by the sheet of charge. Now, what we're going to do, if we go back, part B asked, what if I took a mass that had a charge of +1 nanocoulomb, and I want to float it? at a point 1 centimeter above the sheet. So what's my test charge now? What's the thing being pushed? Yeah, it's gonna be this 1 nanocoulomb, this little point charge that has a mass as well. Now, let me get back to where we were. No matter how we find the electric field, we can always do step 2 with this equation here. It always works. Okay, so all I have to do is take the electric field that I found here and multiply it by the test charge. So I want to float this thing, and that means I want my weight force to be equal to the electric force that's repelling that test charge. Well, that force by the plate on the particle, I can find by just taking the size of the test charge times the electric field. We were told that the test charge was 1 nanocoulomb, or 1 times 10 to the minus 9 coulombs. We just calculated the electric field to be this big. And when I multiply those two together, I get 9.2 times 10 to the minus 4 newtons. Now, if I want this to hover with 0 acceleration, that means I want the weight of that particle to also be 9.2 times 10 to the minus 4 newtons. What part B of this problem asked you is what's the mass? It didn't ask what's the weight, it asked what's the mass. Now that's a 105 problem that we worked a million times. Tell your neighbor how you find the mass if you know the weight. Really quick.
Just move the decimal place.
Newton's per meter.
Acceleration.
Had a train whistle that goes,
Assuming
I
you're
lost it in the move.
Right.
Oh. Okay. So,
Yeah, how do we?
I use the fact that the weight is just the mass that I'm looking for times G, which is 9.8. We call it 10 in this class. And so that's going to give me the mass, which is this value divided by 10, or 9.2 times 10 to the minus 5 kilograms. See if your neighbor's understanding that problem. He's in the way.
He just uses 10.
Yeah.
Acceleration.
Questions? Okay, now, a single plate of charge is not the most common situation. Typically, what we find instead are 2 plates of charge, 1 positive and 1 negative. And they have equal and opposite charge densities. Now, the reason they're equal and opposite is that we usually start with a neutral set of plates and we hook them to a battery. And the battery steals electrons from one plate and dumps it on the other plate. So for every electron that it steals from one plate, it leaves a naked proton behind. And so I've got the same number of extra electrons on one plate as extra protons on the other. And so what we get are 2 plates. And so I want you to just concentrate on the left here. If I had a positive plate, my field lines would be going away and they would be parallel. If instead I had a negative plate, they would be going towards and they would be parallel. If I combine that, if I put that together, what I get is, well, I have to use superposition, okay? If I look at this point here, I have a contribution away from the positive plate, and I have a contribution towards the negative plate. And that's my total. I add them up. Now, you'll notice I drew those 2 arrows the same length on purpose. Why? Tell your neighbor why. How can I be sure those are the same size?
plates. And they're the same charge. Like if the negative one was -2 here.
Okay. I hope you just told your neighbor, I got the same size sigma in both cases. And that's all the electric field depends on. It doesn't depend on distance. And so those two contributions have to be exactly the same size. And it doesn't matter where I look between the two plates, because distance doesn't matter. I've got a contribution away from the positive towards a negative. I get exactly the same answer there as I had down here. And indeed, I'm going to get that same answer everywhere I look between the plates. Everywhere. Exactly the same. If, on the other hand, I look outside the plates, now I get something very different. I get something away from the positive, but now that's down. And I get something towards the negative, and that's going to be up. And so because distance doesn't matter, this is going to be the same size as that, and that's going to cancel out and give me 0. Likewise, I would get 0 above the top negative plate. Now, this is a very useful configuration. What I have with these two parallel plates, equal and opposite, is a uniform electric field in the inside and 0 electric field outside. And if you're doing an experiment where you need an electric field that's uniform, and you don't want any field outside of your experiment to be messing up your electronics, this is the way to go. And so that's why we see this configuration fairly often. Now, how big is that electric field? Well, again, we can use superposition. We remember that it's really two contributions, one from the positive plate and one from the negative plate. And I know how big those contributions are. Okay, there's my formula that I just put on the board. Sigma over epsilon with a half in there. Now, why did I put the half in there? Why did we define epsilon naught the way we did instead of just bringing that 2 in and getting rid of that half? I'll show you why. I've got the same contribution from the negative plate. Now I want you to rename this term sigma over epsilon naught, okay? Let's call it instead apple pie, okay? So I've got half an apple pie, and I got half an apple pie. What have I got? I got an apple pie. Does that make you hungry? Yeah. So what we get when we add that together is sigma over epsilon naught. And because this is the more common situation, that's why we leave the 2 in this equation here. So there are more fundamental reasons for leaving it out of epsilon naught. We won't go into that. So this is going to be for 2 plates equal but opposite.
Yeah, same magnitude.
So in other words, I've got a plus sigma and a minus sigma. In that case, I've got an E field and it has magnitude sigma over epsilon naught. And so here epsilon naught is going to be 8.8 times 10 minus 12 squared, and here the K is equal to 9 times 10. Okay. Now, those are the 3 ways that we can make electric field. And regardless of how we make the electric field, whether we make it with a point source or a single sheet or 2 sheets equal and opposite, we can always use this equation in the end as our last step to find the force. Okay. Now, what do the field lines look like between those sheets? I've got a zero inside and outside, I've got a zero field outside, and I have sigma over epsilon inside. And if I want to represent that with field lines, well, to represent a zero electric field, I use zero field lines. And to represent a uniform electric field, I put parallel field lines. And so this is what the field lines would look like between two plates, equal and opposite. Check that your neighbor is still on the bus. Do a buddy check.
That makes sense.
Yeah. A little trip. Large. Yeah. I'm kind of curious. I'm sure there's.
Okay,
Well,
let's do another clicker question. This is problem 45 in the textbook. Points A and B are located as shown between two large uniformly charged parallel plates, one positive, one negative. Which of the following correctly describes what happens to the electric fields at A and B if the plate on the right is suddenly removed? Your choices are the field at A drops more than the field at B, the field at B drops more than the field at A, both fields remain the same, both fields drop by the same amount. Again, I'll get you started. Okay, now you can click.
like that. Yeah, that happens like.
It would stay the same. It really does.
They should drop this.
Okay, last call. Pick your points. Okay,
Oh, they would change.
She says.
good. The answer is D. The answer is D. Okay, in both of those locations, the field would drop by a factor of 2. Whatever it was, it'd be half as strong once that second plate was removed. Okay, let's talk about conductors. I went out of my way to address like that guy right there. Conductors. But first, let's look at another problem in your homework for Friday. 4.3. A point charge is fixed in place, glued to the sky. It's 3 microcoulombs. It's going to be different in the homework. It's 3 microcoulombs in my slide. And it's in front of a large, the keyword there is large, plastic sheet that contains a uniform surface charge. When an electron is placed halfway between the point charge and the sheet, it feels no electric field. So first of all, what's the electric field at the X? 0. But the electric field due to the point source is not 0. Okay, if we want to find that, we're going to use one of these equations up here. Indeed, since it's a point source, I would use the equation for a point source. And I would say the electric field due to that 3 microcoulombs is going to be equal to K QS over R squared. And in this case, we're told that R is 20 centimeters. Okay. And so I'm going to get 9 times 10 to the 9 times 3 times 10 to the minus 6 divided by 0.2 squared. I'm going to get 6.75 times 10 to the 5th. Okay. If I did that right. I did. Now, I know that that field is away from a positive source, okay? If the total electric, are there questions there? Did I lose anybody? Okay. Is my math right? Someone check that. Good, okay. Now, if I want the electric field at the X to be zero, that tells me immediately that the electric field due to the sheet has to be to the left or away from the sheet. So that immediately tells me that sheet has to be positively charged. And the sigma has to be a positive sigma. So now, if I use this second equation for a single sheet, E is equal to sigma over 2 epsilon naught. I can rewrite that as sigma is equal to 2 epsilon naught times E. That's going to be 2 times 8.85 times 10 to the minus 12. E we said was 6.75 times 10 to the 5th. And that's going to give me 9 times 9. No. Let me remind myself. 1.2 times 10 to the minus 5 coulombs per meter squared. Did I do the math right there? Okay. Now, now things get dicey. Now we take a metal block that's neutral and we shove it right there, right behind the sheet of charge. And we're first asked, if that's a metal block and the electrons are free in a metal to swim to their happy place, where are the electrons going to swim to if I've got this big positive charge there, and more importantly, this huge sheet of positive charge right there, close to it? Yeah, they're going to swim close to that positive charge to the left. Well, now I have 4 Klingons in this problem, 4 sources of electric field. I have the electric field, the purple one, due to that one, the 3 microcoulombs. I have the blue electric field due to the sheet. And now I have an electric field in dark blue due to the electrons and an electric field in dark green due to the naked protons. And again, I drew the dark blue arrow longer than the dark green one. Why? Because the charge is concentrated. This isn't a big sheet of charge. This is a small concentration. So distance matters. Okay, and so now when I add those up together, I get a net electric field to the right. But wait a minute, Greg. Wait a minute. They said there's an electron at the X. An electron's negative. Wouldn't the electric field care about that? No or heck no? Heck no. The electric field doesn't care about what's being pushed. It only cares about the charges that made the electric field, which is everything except what's being pushed. Okay. The last part of this problem asks, what direction would the electric force point on that electron? And that's where we use this vector equation. If the electric field, the total electric field is to the right, and I multiply that by a negative test charge, well, multiplying a vector by negative switches the direction. And so that means the force on that negative electron, whoops, is going to be to the left. I thought I had it on the slide, but I made a mistake. That's one mistake. If I make 3 mistakes, you get your tuition back. Okay. But I have to admit that they're mistakes. He's doing. Other questions on that problem? Yes, sir.
So if it was right next to the conductor, right next to that metal block, would you treat that more as a plate?
Sam.
Right next to the conductor, we treat it as like an infinite sheet.
Oh, yeah, if we were looking right super close to the conductor, then we'd treat it as an infinite sheet. So, but I'd never do that to you on a homework or an exam. It's always going to be pretty clear. You know, I'll always use words like a very, very large sheet.
Which is to the left because.
Right, and so again, if we're careful with our equation. If this is to the right. And this is negative.
There is one.
Then the direction here is gonna be negative, right? It's just another way of saying. Okay. Suppose I have two infinite sheets. One that comes out and splits the class, and the other one that goes above your head out here. And I want to find the electric field at that point 1. And I'm going to give you 3 choices, A, B, or C, with your clicker. Which of those is the correct? You can click. Is it A, B, or C for the direction of the electric field? Okay, last call. We get to 148. Close enough. Okay, good. The answer is B. And what you used there, I hope, was symmetry. Okay, it just there's no reason why it would be anywhere away from 45 degrees, given the symmetry of that problem. If I were to take a mirror and put it at 45 degrees, the problem would look the same. And so my solution had better look the same in the mirror. Now, again, symmetry. One day, Greg, I'll be sitting at that desk. If I can't tell the difference in the problem, I can't tell the difference in the solution. So what about point 2 that's closer to that lower plate or the horizontal plate? In that case, would it be A, B, or C with your clicker again? Same.
No.
Okay, last call. Good. The answer is B. I wasn't able to shake you off. If we use superposition and we use the fact that it doesn't depend on distance from the sheet, I get a contribution away from the horizontal sheet. I get a contribution away from the horizontal or the vertical sheet. And it would be exactly the same size because distance doesn't matter. And now when I add those, I get B. Okay. Just checking to see if you really believe that it was independent of distance. Now let's talk about conductors. This purple bar is really a slab of metal coming out towards you, great big slab of metal. And if I take a bucket of electrons and I dump those electrons on that slab, they are gonna quickly go to their happy place. And when I say quickly, just blink as fast as you can. Okay? It takes 10 to the minus 17 seconds for those electrons to get to their happy place, where they're gonna stop. Okay? And you can't blink that fast. That's really fast. That's really fast. Now, I've chosen a very simple piece of metal. I could have had some metal statue of somebody, Abraham Lincoln, okay? But instead I chose something simple because you know the answer to this because of symmetry. You know that their happy place is they're gonna wanna get as far away from each other as possible. And the way to do that is to go to the outer surfaces, half to the left, half to the right. And I wouldn't expect more than half to go one direction because the two sides look the same. Symmetry, symmetry. Well, now, if I started with a sigma that was sigma naught, that's total charge divided by the total area of this big old hunk of metal. I've only got half that sigma on the left, and I've got half of that sigma on the right. Okay? Now, if I look at the electric field inside the conductor, inside the metal, you know what it's going to be. Because I've got a contribution, if I use superposition, towards that negative sheet. And I have another contribution. That's the size of that contribution. And if I put in sigma naught instead of sigma L, I get another factor of a half. And on the right-hand side, I get exactly the same size field pointing the other direction towards the negative sheet. And that adds up to 0. Okay. Now, I've done that for a very, very simple configuration or size, piece of metal. But no matter how complex, it could be the most intricate metal statue you could imagine. If I'm willing to be patient and wait 10 to the minus 17 seconds, the electric field everywhere inside that metal is going to be 0. Why? Because electrons are free to flow inside a metal. If they've stopped flowing, there must no longer be an electric field pushing them. And so they're gonna flow to a place where they can cancel out the electric field inside the metal. And then they're gonna stop. Okay, and that happens very, very quickly. And that's the key idea about metals that you need to know, is that inside a metal, the electric field has to be 0. Now, outside of this metal slab, one more thing that you need to know. And that is, the electrons are also free to flow on the surface of a metal object. And so if I had an electric field that was tangent to the metal surface, the electrons would still be pushed by that. They'd still be moving. And so that means once they get to their happy place, the electric field has to always be pointing in a direction 90 degrees to the surface of the metal. And we're going to find next week that that's why I get a very strong electric field near a sharp point. Okay? So we call this electromagnetic shielding. In Montana, we had a laboratory up on the 4th floor where students were creating CubeSats, little tiny satellites that were going to go up in a rocket with an experiment inside. And the last thing that they would do when they were finished putting their experiment inside was wrap that experiment in aluminum foil. And indeed, they use a whole lot of aluminum foil at NASA. My brother-in-law works at VAST, where they're creating a space station that's got gravity due to rotation. They're getting close to launching a prototype. The amount of aluminum foil that they have there is just amazing. Essentially to shield out the external fields. Okay. Now, I have a demonstration to show you. I'm going to put the lights up. In order to understand this demonstration, you need to understand an electroscope. This is a simple electroscope here, where we just have two pieces of foil connected to a metal rod with a metal ball on top. And this central structure is insulated from everything else. The glass jar and the rubber stopper are just support pieces, okay? And when we put charge on the metal ball, it spreads out and goes down to those sheets of aluminum, and they want to get as far apart from each other as possible, so they spread out. Well, we've got a little bit different configuration. There we go. We have this device here that you people can see, but you people can't. You'll have to look at the screen there, and maybe I'll just put it on both screens. Now, what we have, you want to ignore this circle because that's just a support mechanism. The important piece of this device is this little bar that's got yellow on it, and it's free to rotate, okay, about a pivot there. And this metal bar that goes up to a metal top up here. Okay. Now, if I take a rubber rod and I charge it. Now, the rubber rod is a non-conductor, an insulator. And so wherever I put extra charge, extra electrons, they're stuck. So if I want to get a lot of electrons off of this thing, I've got to scrape that like I'm scraping peanut butter off of a knife. Okay. And then you see I get those to repel each other. Now I can neutralize that by touching it to a large conductor, and oh look, I'm a large conductor. I just neutralize that. Okay, now what I'm going to do is I'm going to start with that's neutral. Put that over there. I'm going to start with this Wimhurst machine. And a Wimhurst machine uses a little bit of complicated, an idea that we'll talk about next week called induction. To separate charge, you're just going to put electrons in one of these, we call this a capacitor or a Leyden jar. It's just a storage jar. I'm going to put electrons in one and leave a lack of electrons in the other. And when I get a big enough charge separation, I'm going to throw an arc. Now, in Montana, we have to crank it, and but we've got modern technology here at BYU. Oh. You see it? You're convinced there's enough charge to throw a spark? Okay. Now, what I'm going to do is I'm going to use that device to dump electrons straight down into this metal can, and the metal can is going to start out neutral. I know it's neutral because I just touched it. Okay, and I'm gonna take this metal chain. Solid gold, it's worth about $60,000. We use your tuition. Oh, it's not. Okay, and I'm just going to dump electrons into the middle of this bucket. Now, I call it a bucket because this experiment was first done by Michael Faraday, and this is typically called Faraday's bucket because he used a milk bucket to do this demo. So I am dumping a whole bunch of electrons into the inside of that bucket. Now I'm going to take this non-conductor and I'm going to use that to just drop that into the middle there. And then I'm going to take this conducting ball and I'm going to rub it around the inside. And lo and behold, nothing. Okay. Well, where's the charge? Well, I'm not sure it's here because I just felt a spark on my hand, but let's see. Nothing. I felt a spark. I need a longer rod. Let's do that again. Okay. Fired it up. This time I won't let myself get zapped. Okay.
Probably keeps it.
Very careful. Now, we saw that inside there was nothing. But on the outside. I was looking for. That's what I was looking for. Okay. An excess charge is going to go to the outside of what we call a Faraday cage. It's always going to go to the outside. And that's why when you're in a lightning storm, the safest place that you can be is inside your metal car, the body of your metal car. If you've got a Corvette Stingray, you're toast. It's folks, I see that you're anxious to get to that emotional today. Why don't we stop here and go to the emotional? Nothing on your head.
It's Elder Stevenson, right?